Coulomb's law says that the force F between two charges Q1 and Q2 separated by distance r has a magnitude given by this relationship. This applies to point charges. Q1 and Q2 have to be point charges. If Q1 and Q2 aren't point charges, then Coulomb's law doesn't apply. Although if Q1 and Q2 are nearly point charges, for example, two square or rectangular pieces of tape separated by a distance that's greater than the dimensions of the tape, much greater than the dimensions of the tape, then the one part of one tape is not too much further from any part of the other tape, or any 2 points, one point on this tape and one point on this tape, will be separated by about the same distance, and we can still apply Coulomb's law to a good approximation. However, if we have two capacitor plates, one plate here and one plate here, then the charges on the plate over on this side are not at a uniform distance from the charges on the other plate. Different parts of the plates are separated by different distances, and we can't make the approximation. So in any case, Coulomb's law applies to point charges, and the vector form of Coulomb's law is given here. We take the absolute value signs from around the force vector, and actually this force here ought to be a vector, shouldn't it? Okay. We take the absolute value signs away from the force vector. We use the same expression for the magnitude of the force, but we multiply it by this unit vector, r over the magnitude of r. And of course we've been over this. This is just a unit vector in the direction from charge 1 to charge 2. And actually we've used the subscript 1, 2 on that vector to indicate that it's from charge 1 to charge 2, and F1, 2 to indicate that that's a force on charge 2 exerted by charge 1. Now you can review the original presentation of this idea, but that's an important law and an important idea. Now once we have Coulomb's law, at least for a system of point charges, we can define the voltage between 2 points A and B. Okay, the voltage from point A to point B, the voltage difference, is the work we've got to do to go from point A to point B divided by the charge that we move from point A to point B. So we imagine moving a charge from point A to point B. We've got to do a certain amount of work, which we'll indicate by delta WAB, and then we divide that by the test charge. Okay, this is the work per charge to move from point A to point B. It turns out, and we don't prove it in this course, it really requires multivariate calculus to prove the idea, but the work done in moving from point A to a point B in an electrical field is independent of the path followed by the test charge. Therefore, the voltage between A and B is well defined. That means the voltage between A and B is the same no matter what path you use to go from A to B.